Download this code from codegive.com, link in the description below. OK, let's dive into the fascinating world of adaptive music. This tutorial will cover the concept, its scope, various techniques, implementation strategies, and provide code examples in Python, using the pygame library for audio playback, and a conceptual example in Max/MSP, a visual programming language for audio. Table of contents. 1. What is adaptive music? 2. Why adaptive music? Scope and applications. 3. Adaptive music techniques. 3.1 Branching and layering. 3.2 Sequencing and compositional algorithms. 3.3 Reactive sound design. 3.4 Parameter mapping and control. 3.5 Generative music. 4. Implementation strategies. 4.1 Game engines and middleware. 4.2 Standalone systems. 4.3 Using scripting languages. 5 Code examples, Python and pygame. 5.1 Basic audio playback. 5.2 Adaptive branching. 5.3 Adaptive layering. 5.4 Simple parameter-based adaptation. 6 Conceptual example, Max/MSP. 7 Challenges and considerations. 8 Beyond the basics, advanced techniques. 9 Conclusion. 1. What is adaptive music? Adaptive music, at its core, is music that changes in response to some external input or condition. Instead of being a static, pre-recorded piece, adaptive music dynamically evolves, reacting to real-time data or events. This data can be anything from user interaction in a game or VR experience to sensor data from a physical environment, or even algorithmic decisions based on game state or character behavior. The primary goal of adaptive music is to create a more immersive, engaging, and personalized listening experience. It enhances the user's connection to the content by making the music feel like an active participant in the narrative or environment, rather than a passive background element. 2. Why adaptive music? Scope and applications. The potential applications of adaptive music are vast and span multiple domains. Video games. Adaptive music is most commonly used in games to intensify dramatic moments, reflect the player's actions, match the emotional tone of different environments, and provide cues. Examples include transitioning to more intense music during combat, altering the music's mood in a peaceful area, or providing audio feedback for player actions. Virtual reality, VR, and augmented reality, AR. Adaptive music can react to the user's gaze direction, movement, or interactions with virtual objects, enhancing the sense of presence and immersion. For example, if the user looks at a sad character, the music could become more melancholic. Interactive installations. Museum exhibits, art installations, and public spaces can benefit from adaptive music that responds to the presence and movement of visitors. Sensors can trigger changes in the musical arrangement, creating unique and personalized experiences. Wellness and therapy. Adaptive music can be used in therapeutic settings to help patients relax, manage stress, or improve mood. Biometric data, such as heart rate or skin conductance, can be used to dynamically adjust the music's tempo, harmony, and instrumentation. Automotive. Adaptive music can be integrated into vehicle systems to respond to driving conditions, driver behavior, or passenger preferences. It can adjust the music's intensity and tempo to match the speed of the vehicle or provide alerts. Personalized soundtracks. Adaptive music could be used to create personalized soundtracks for users based on their mood, activity level, or location. The advantages of using adaptive music are significant. Increased immersion. Music that reacts to the environment or user actions creates a stronger sense of presence and immersion. Enhanced emotional impact. Adaptive music can amplify the emotional impact of events and scenes. Dynamic and engaging experiences. Adaptive music prevents repetition and monotony, keeping the listening experience fresh and engaging. Personalization. Adaptive music can be tailored to individual preferences and contexts. Narrative integration. Music can be seamlessly integrated into the narrative of a game, film, or other interactive experience. 3. Adaptive music techniques. There are several approaches to creating adaptive music. 3.1 Branching and layering. Branching. This involves creating multiple variations, or segments, of a song and then transitioning smoothly between them based on specific triggers or conditions. These transitions can be abrupt, hard cuts, or subtle, crossfades. Layering. This involves creating individual musical layers, example melody, bass line, drums, harmony, and then adding or removing them based on the current state. Layering creates variations in intensity and complexity without requiring completely different song structures. Example, branching. A game might have a peaceful music loop for exploration, a tense loop for stealth, and a high-energy loop for combat. The game logic determines when to switch between these loops based on player actions and enemy encounters. Example, layering a soundtrack for a relaxing VR experience might start with ambient pads and nature sounds. As the user interacts with objects, more layers, example melodic elements, rhythmic patterns, are gradually introduced. 3.2 Sequencing and compositional algorithms. Sequencing. This involves using a predefined sequence of musical events, such as notes, chords, or rhythms, and then dynamically modifying the sequence based on input data. You can change the tempo, key, or instrumentation of the sequence to create variations. Compositional algorithms. These are computer algorithms that generate music based on a set of rules and constraints. These algorithms can be used to create original musical material in real time, adapting to user input or other environmental factors. Example, sequencing. A music application could use a predefined melodic sequence and then transpose it based on the user's input, allowing them to create melodies in different keys. Example, compositional algorithms. A generative music system for an art installation might use Markov chains or other statistical models to generate music based on the movement of visitors. 3.3 Reactive sound design. This technique focuses on creating sound effects and sonic textures that respond to specific events or actions. This can involve modifying the pitch, volume, timbre, or spatialization of sound effects to create a more immersive and reactive experience. Example, the sound of a footstep might change based on the surface the character is walking on, the character's speed, and the environment's acoustics. 3.4 Parameter mapping and control. This involves mapping external parameters, example player health, enemy density, environmental conditions, to musical parameters, example tempo, volume, reverb, distortion. This allows you to dynamically control the music's characteristics based on the state of the environment or the user's actions. Example, a racing game might increase the music's tempo and distortion as the player's speed increases. 3.5 Generative music. Generative music utilizes algorithms, rules, and randomness to create music in real time. It's less about pre-composed elements and more about musical systems capable of producing varied and evolving outputs based on defined constraints and input data. This is often combined with other techniques. Example: a generative system could define melodic rules that evolve based on the current time of day, creating a dynamically changing ambient soundscape. 4. Implementation strategies. 4.1 Game engines and middleware. Game engines, Unity, Unreal Engine. These engines provide built-in audio tools and scripting capabilities that allow you to implement adaptive music directly within the game environment. You can use scripting languages like C, Unity, or C++, Unreal Engine, to control audio playback, layering, and parameter mapping. Audio middleware, WIS, FMOD audio middleware provides a more advanced set of tools for managing and controlling audio in games. They offer features such as interactive music systems, sound effect design, and spatial audio processing. Middleware often requires programming, but provides a graphical interface to organize and manage audio assets. 4.2 Standalone systems. You can create standalone adaptive music systems using programming languages like Python, Java, or C++. These systems can be integrated with external sensors or data sources to create interactive musical experiences. This approach offers the most flexibility but requires more programming expertise. 4.3 Using scripting languages. Scripting languages like Python can be used to prototype and experiment with adaptive music concepts. Libraries like pygame, for basic audio playback, or more advanced libraries like Librosa, for audio analysis and manipulation, can be used to create dynamic musical systems. 5. Code examples, Python and pygame. Important: make sure you have Python and pygame installed. You can install pygame using pip install pygame. Explanation: pygame.mixer this module handles audio playback in pygame. Pygame.mixer.sound represents a loaded sound file. Pygame.mixer.channel allows you to play multiple sounds simultaneously on separate channels, enabling layering. Sound.play plays the loaded sound. Channel.play plays the sound on a specific channel. The loops argument controls how many times the sound repeats, -1 for infinite loop. Channel.stop stops the sound playback on the channel. Channel.set_volume controls the volume of the sound on the channel. Adaptive branching the code asks the user for input and plays a different sound file based on their choice. Adaptive layering the code sets up 4 audio channels and allows the user to add or remove layers, melody, harmony, effects, by pressing keys. Parameter-based adaptation simulates a parameter and maps it to the volume of a sound using channel.set_volume. Important notes: replace peaceful_loop.wave, tense_loop.wave, bass_layer.wave, melody.wave, harmony.wave, effects.wave, and instrument_loop.wave with the actual paths to your audio files. Make sure the files are in a compatible format, example WAV, MP3. For adaptive branching and layering to work effectively, your audio loops should be designed to transition smoothly or complement each other. This is a basic example. Real-world adaptive music systems are far more complex. The pygame.time.delay function can be used for precise timing and synchronization. 6. Conceptual example, Max/MSP. Max/MSP is a visual programming environment that's excellent for prototyping adaptive music systems. Here's a conceptual outline of how you might implement adaptive layering in Max/MSP. 1. Load audio files * use the buffer object to load individual audio files, layers, into memory. These could be loops of different instruments or musical elements. 2. Control volume with gain * each buffer object would be connected to a gain object, which controls the volume of the layer. 3. Create a user interface * use slider objects or button objects to control the gain of each layer. These objects would provide a graphical interface for adjusting the volume levels. 4. Implement logic * use if statements, select objects, or other logic components to dynamically change the volume of each layer based on external events or user input. For example, a sensor could trigger an increase in the volume of the drum layer when a person enters a room. 5. Master output * mix the outputs of all the gain objects using a plus object and send the result to the audio output, as DAC or ADC. Example patch, conceptual. Explanation * buffer, loads the audio file. * gain, controls the volume of the audio. * plus, mixes the audio signals. *DAC, sends the audio to the speakers. * slider, provides a visual control for setting the volume. * metro, generates a regular pulse. * random, generates random numbers. This is just a very simple example. More complex algorithms can be used for music generation. **** multiplies the output of the random object by a value. This is a simplified representation. In a more advanced Max/MSP patch, you might use sec objects to control the timing and sequence of notes, cycle objects to generate waveforms, and more sophisticated algorithms to create generative music. 7. Challenges and considerations. Creating effective adaptive music is challenging. Some key considerations. Smooth transitions transitions between different musical segments or layers need to be seamless to avoid jarring changes in the listening experience. Techniques like crossfading, beat matching, and key modulation can help create smooth transitions. Variety and avoidance of repetition. Adaptive music systems should be designed to provide enough variety to avoid becoming repetitive or predictable. This can be achieved by using a large library of musical assets, generative algorithms, or dynamic parameter control. Computational cost. Real-time audio processing can be computationally expensive, especially for complex generative music systems. It's important to optimize the code and algorithms to ensure that they can run smoothly on the target hardware. Design coherence. The adaptive music system should be designed to complement the overall experience. The music should enhance the narrative, atmosphere, or gameplay without being distracting or intrusive. Balancing control and autonomy. The system should respond in a way that feels natural and intuitive, not overly reactive or random. Finding the right balance between predefined rules and algorithmic generation is crucial. Memory management. Loading and storing large audio files can consume a lot of memory. Efficient memory management techniques should be used to avoid performance issues. 8. Beyond the basics, advanced techniques. AI-powered composition. Using machine learning to analyze and generate music based on user input or environmental data. Real-time audio analysis. Analyzing the audio signal in real time to extract features such as pitch, tempo, and timbre, and then using these features to control other musical parameters. Libraries like librosa in Python allow for this type of real-time analysis. Procedural audio. Generating sound effects and musical elements algorithmically, rather than relying on pre-recorded samples. Spatial audio and 3D soundscapes. Using spatial audio techniques to create immersive and dynamic soundscapes that respond to the user's position and orientation in a 3D environment. 9. Conclusion. Adaptive music is a powerful tool for creating immersive, engaging, and personalized audio experiences. By carefully considering the techniques, implementation strategies, and challenges outlined in this tutorial, you can create dynamic musical systems that respond to the environment, user actions, or other real-time data. Experiment with the code examples provided and explore more advanced techniques to unlock the full potential of adaptive music. The possibilities are truly limitless. Remember to create your own audio files and replace the placeholders in the example code. Good luck.